Morning, y'all. Today we're going to be talking about inverse trigonometric integrals. Wow, I cannot talk today. Today we're going to talk about inverse trig integrals. And while with derivatives, we talked about all 6 of our inverse trig functions, with integrals, we're really only going to talk about these main 3. So all of our cosecant, cotangent, cosine, we're really not going to talk about those. They're not really going to show up that often. They do also have their own formulas, but just like as we kind of start to get to the end of both derivatives and integrals, we go over some of the more obscure formulas. Same idea here with our inverse trig integrals. Okay, so up there at the top, you'll see the 3 that we're going to talk about: arcsine, arctan, and arcsecant. And you should see the integrals that we're looking for are essentially those derivative rules. Arcsine was the square root. Arcsecant was the square root with the extra multiply by u. And then tangent was just the very basic 1 over 1 plus x squared usually. So a in all of these is taking the place of some constant. So a is equal to some constant. And then u, of course, is our actual function. Okay, just like normal u for our u sub. So you're probably thinking, well, Mr. Arbone, these are u subs, right? Yes, they are, and you can do u substitution, but we really don't have to go through the full process of u sub for most of these because they're not super convoluted. Like, they don't make them really hard because just remembering the formulas to begin with is pretty hard. So let's look at number 1. So number 1, we have dx over 16 plus x squared. So right off the bat, you should notice this one looks just like tangent. So with tangent, our second piece is our u. Our first piece is our a. Okay? Or I can switch around. Really, it's just the constant is the a. The x term or whatever is going to be your u. Okay? But 16 isn't quite a squared. So before I actually integrate this, I can change this to be dx over 4 squared plus x squared. And that just allows me to apply the formula a little easier. So now I can see that my u is equal to x because it's u squared. So u is just x. My a is equal to 4. And I don't have to really go through the full process of u substitution because u is just x. The derivative of x is dx. du equals dx. I'm not going to get anything extra in here. So just kind of like with some of those log ones that we'd see where it was just the basic u prime over u. This is just the basic du over a squared plus u squared. So I can just straight up apply the formula. So my integral becomes 1 over a, so 1 over 4, arctangent of u over 4, so x over 4, and then plus c. And that's it. Okay, so if it's very basic, just the formula, then these are super, super easy. Now, they obviously do get just a little bit more complicated. So let's look at number 2. So this one is a definite integral. I have limits. Okay. So as I can see, it's dx over the square root of some a value minus an x term. So square root is going to be sine or secant because it doesn't have an extra x term or an extra u out front of it. Then it has to be sine. So we're looking for sine. So the setup's all there. I just need to change my 9 to be my a squared. And x squared is already x squared. So that's good to go. So before I integrate this, I can change this to be the integral from 0 to 2 of dx over the square root of 3 squared minus x squared. And y'all might have already noticed, really this is an extra step. If you can see that 9 is going to be 3 squared, you can just jump straight to your integral. You don't have to go through this rewriting step if you don't want to. So u is equal to x again. And a this time is equal to 3. So then from here, I can go ahead and integrate my integral of dx over a squared minus u squared. Square root of that is just arcsine of u over a. Okay, no extra 1 over a in front. So this becomes arcsine of x over 3, as I did not provide myself any room to write that, of x over 3. And I'm evaluating it from 0 to 2. So instead of that plus c, I'm actually evaluating this. So this becomes arcsine of 2/3 minus arcsine of 0. And to finish this out and evaluate this, remember when you're doing inverse trig or arc trig, you're thinking backwards on the unit circle. So instead of plugging in a radian or degrees value and getting out a unit circle point, I'm thinking at what radians or degrees value would these unit circle points occur? So where on the unit circle where would sine be equal to 2/3? Well, there's nowhere on the unit circle because we know there's 0 and 1, 1/2, root 2 over 2, root 3 over 2, but there's nowhere where 2/3 is one of our nice pretty unit circles. So without a calculator, we can't evaluate arcsine of 2/3. So that one we're just going to leave as is. The second one, arcsine of 0, so we have to think of where on the unit circle is sine equal to 0, where there's two spots, 0 and pi. And then remember, back in pre-AP/Pre-Cal, which you might have forgotten, but with inverse trig, they all had restricted domains because of how we actually find the inverse of a function. And arcsine's restricted domain is from negative pi over 2 to positive pi over 2. So even though 0 and pi are both where sine is equal to 0, only 0 is within that restricted domain of negative pi over 2 to pi over 2. So arcsine of 0 actually does become 0. So my final answer is just arcsine of 2/3 minus 0, which is just arcsine of 2/3. Because I still can't evaluate that, I'm just going to leave it as is. All right, let's bump it up just a bit with 3 and 4. So 3, we have dx over x times the square root of 4x squared minus 1. So now we have that x outside the square root, so we know we're looking at arcsecant. Okay, and just like before, I want to rewrite both my pieces inside to be my u squared and my a squared. So u squared, I want to think of if I take a squared out of that 4x squared, what would I have left behind? So if I do that, not that, I get the integral of dx over still x square roots of, instead of 4x squared, 2x parentheses squared. Because if I squared 2x, 2 squared is 4, x squared is x squared. So 4x squared is also equal to 2x parentheses squared. And then, of course, minus 1 squared, because 1 squared is just itself. So that one's a little easier. Got to get my square root to fit. All right. So from here, you probably can notice that our u is equal to 2x and our a is equal to just 1. Okay, but right now we have an issue. We have 2x on the inside, but our other part where we're supposed to have u, we don't have 2x. So that's a problem. But what I can do is, because I just need this x to be 2x, I can multiply by 2 over 2, which is just 1. So I'm not changing anything about my function. I'm just changing how I see everything in the function. So this becomes the integral of 2 dx over 2x square roots of 2x squared minus 1 squared. So now I have 2x in both the spots I need. I have 1. I'm going to bring that 2 out front just to make it a little easier for me to integrate. So dx over 2x square roots, parentheses, 2x squared minus 1 squared. And now I can apply my integral formula. So this is equal to 2. And then it's 1 over a, so just 1 over 1. Arcsecant and then absolute value of 2x over a, so absolute value of 2x over 1, and then, of course, plus c. So just to write this one more time, make it a little easier to see. 2, 1 over 1, that's just 2 times 1, so 2. Arcsecant, absolute value of 2x over 1, that's just absolute value of 2x. And then plus c. So that one was just a little bit more challenging. There we go. as it had that extra step of multiplying by the 2 over 2. So let's look at one last one, number 4. We have the integral of dx over x squared plus 4x plus 9. And right off the bat, you probably want to look at this one and think arc trig. But this is arctangent. It is that kind of formula of 1 over an a squared plus u squared. But we got some extra stuff. We got this extra 4x term in the middle. Okay, but we are actually going to make it just a little bit easier on ourselves, because what we can do is we can do what's called completing the square. It's a way for us to be able to factor this into something nice and pretty, into something squared, even though I don't actually have a perfect square trinomial right now. So I can change this bottom to be dx over x squared plus 4x plus 4 minus 4 plus 9. And you might be thinking, why would I add plus 4 minus 4? That just cancels out. Well, it does just cancel out, which is why I can do it. It makes it legal, okay? Number 1. Number 2, now I have x squared plus 4x plus 4, which is a perfect square trinomial, which is going to factor into a binomial squared, which gets me that u squared term that I want. So this becomes the integral of dx over x squared plus 4x plus 4 factors into x plus 2 squared. And then I have left over this minus 4 plus 9, which becomes plus 5. Okay, now very last thing, I have my u squared. I would like to have my a squared, so I can also write 5 as the square root of 5 squared. So I just have to change it to a number being squared for me to be able to apply my formula. So that's why I'm taking the squared of the square root, which seems redundant, but it's just so I can apply my formula. So this becomes dx over, not through dx, dx over x plus 2 squared plus the square root of 5 squared. And then from here, I see that my u is very clearly x plus 2. And I see that my a is very clearly root 5. So I had to do some extra little work at the beginning, but eventually I get it to my formula. So then I can apply my formula. So tangent is 1 over a times arctangent u over a. So 1 over root 5. Arctangent of x plus 2 over root 5. And then, of course, plus c. And you could leave it like that if you wanted to. More than likely, if this one popped up, it would pop up in some sort of free response question. If you wanted to rationalize everything, though, you could. So this would become 5 root 5 over 5. Arctangent. I'm sorry, just root 5 over 5. So root 5 over 5 arctangent. Root 5 x plus 2 over 5. And then, of course, still your plus c. And that would be it. So just a little extra step if you want to rationalize, but you don't have to. Okay, so this is inverse trig integrals. I recognize that they're pretty difficult and probably kind of confusing. They're also kind of hard to recognize. I mean, some of them can be really obvious and clear. Some of them can be not so obvious, like number 4. Okay, they don't show up a ton. I don't want you to fret and really worry about them. They're not going to be on your quiz. They're not going to be on your test. I just wanted to throw them out there, especially for those of you really shooting, for everything. I wanted to make sure we don't skip over it. But that is inverse trig integrals.